Imagine a time before time existed, a time when there was no past, no future, just an endless void of nothingness. A time before space itself, where the concept of distance and direction had no meaning. This was the state of the universe 20 billion years ago, a time so distant it's almost beyond comprehension. Then, in a fraction of a second, everything changed. In an event that defies the limits of our imagination, the universe was born. The Big Bang, an unimaginable explosion of energy, marked the birth of our universe. It was not just an explosion in space, but the creation of space itself. From this point of singularity, everything we know, space, time, matter, came into existence. The very fabric of reality was woven in that instant. The universe was a hot, dense soup of energy and particles, expanding at an incredible rate. It was a chaotic, seething mass of potential. As it expanded, it cooled, setting the stage for the formation of the universe we know today. The cooling allowed particles to combine and form the first simple atoms. The Big Bang wasn't an explosion into an existing space. It was the expansion of space itself, a stretching of the very dimensions of existence. Picture a balloon with dots on it. As you inflate the balloon, the dots move farther apart. This is similar to how galaxies are moving away from each other as the universe expands. The universe is like that balloon, constantly expanding, with galaxies drifting apart as space itself stretches. This expansion is not just a theory, it's supported by a wealth of evidence, including the observed redshift of distant galaxies. The redshift is like a cosmic Doppler effect, showing us that galaxies are moving away from us and from each other as the universe expands. Another piece of evidence is the cosmic microwave background radiation. This faint glow, a remnant of the Big Bang, fills the universe. This radiation, a faint afterglow of the Big Bang, provides a snapshot of the early universe, a baby picture of the cosmos. It tells us about the conditions of the universe just moments after its birth, offering clues to its origins and its ultimate fate. As the universe continued to expand and cool, gravity began to pull matter together, forming the first stars and galaxies. These early structures were the building blocks of the complex universe we see today. Over billions of years, these stars and galaxies evolved, giving rise to the rich tapestry of cosmic structures we observe now. From the smallest particles to the largest galaxy clusters, everything we see today traces its origins back to that singular moment of creation. As we look up at the night sky, we are not just seeing distant stars and galaxies. We are witnessing the history of the universe, a story written in light that has traveled across billions of years to reach us. The universe continues to expand, and its future remains a subject of great curiosity and study. Will it keep expanding forever, or will it eventually collapse back on itself? These are questions that drive the quest for knowledge and understanding. Scientists around the world are dedicated to unraveling these mysteries, using advanced telescopes and observatories to peer deeper into the cosmos than ever before. Each discovery brings us closer to understanding the true nature of our universe. The journey to understand the universe is a cosmic adventure, one that spans the vastness of space and the depths of time. It is a journey that connects us to the very beginning of everything and to the future that lies ahead.
In the first few minutes after the Big Bang, the universe was a cauldron of energy. This was a time of unimaginable temperatures and densities, where the very fabric of space and time was being shaped. The energy was so intense that it was almost impossible to distinguish between different forms of matter. As it cooled, energy began to condense into matter, following Einstein's famous equation E=mc². This equation, one of the most well-known in physics, tells us that energy can be converted into matter and vice versa. It was this principle that allowed the universe to transition from a state of pure energy to one where particles could form. This equation tells us that energy and matter are interchangeable, two sides of the same cosmic coin. In the early universe, this interchange was happening constantly, with particles and antiparticles being created and annihilated in a cosmic dance. This dynamic interplay set the stage for the formation of the first stable particles. The first elements to form were the simplest hydrogen and helium. These elements are the building blocks of the universe, making up about 99% of its visible matter. Hydrogen, the lightest element, consists of just one proton and one electron, while helium has two protons, two neutrons, and two electrons. These elements, forged in the intense heat of the early universe, would become the building blocks for stars and galaxies. The process of their formation was a delicate balance of forces, with gravity pulling particles together and thermal pressure pushing them apart. Gravity, the architect of the cosmos, began to pull these elements together. Over time, regions of higher density formed, leading to the creation of vast clouds of gas and dust. These clouds, known as nebulae, are the birthplaces of stars and planets. Clouds of hydrogen and helium collapsed under their own weight, creating regions of immense density and pressure. In these regions, the conditions were right for nuclear fusion to begin. This process, where lighter elements fuse to form heavier ones, releases a tremendous amount of energy. These regions became the nurseries of stars, where nuclear fusion ignited, flooding the universe with light and heat. The first stars were massive and short-lived, burning through their fuel quickly and ending their lives in spectacular supernovae. Stars, the cosmic furnaces, would go on to create heavier elements through nuclear fusion in their cores. Elements like carbon, oxygen, and iron were forged in the hearts of stars, and when these stars died, they scattered these elements into space. These heavier elements, such as carbon, oxygen, and iron, would eventually become the building blocks for planets and ultimately life itself. The elements created in stars are the same ones that make up our bodies, the air we breathe, and the ground we walk on. In this way, we are all made of star stuff, connected to the cosmos in a profound way.
About 4.6 billion years ago, in a remote corner of the Milky Way galaxy, our solar system began to form. This was a time of immense cosmic activity, with stars being born and dying, and galaxies colliding and merging. A giant cloud of gas and dust, called a solar nebula, collapsed under its own gravity. This collapse was triggered by a shock wave from a nearby supernova, which caused the nebula to spin and flatten into a disk. At the center of this swirling disk, the sun ignited, bathing the surrounding space in light and heat. The ignition of the sun marked the birth of our solar system, providing the energy needed for the formation of planets. Dust and gas in the nebula began to clump together, forming planetesimals, the seeds of planets. These planetesimals collided and merged, growing larger and larger over time. One of these planetesimals, destined to become our home, was Earth. In its early stages, Earth was a chaotic and violent place, constantly changing and evolving. Early Earth was a hellish place, a molten ball of rock constantly bombarded by asteroids and comets. These impacts generated immense heat, keeping the surface in a molten state. Volcanoes erupted across the surface, spewing lava and gases into the atmosphere. These volcanic eruptions played a crucial role in shaping the planet's surface and atmosphere. Over millions of years, Earth began to cool. As the planet cooled, the molten rock solidified, forming a solid crust. The bombardment slowed, and a solid crust formed. This crust was the foundation upon which the continents and oceans would eventually develop. Water vapor in the atmosphere condensed, forming oceans that covered much of the planet's surface. These early oceans were crucial for the development of life, providing a stable environment for chemical reactions to occur. The stage was set for the emergence of life. With a stable crust and abundant water, Earth was ready to host the first living organisms, setting the stage for the incredible diversity of life we see today. Section 4. The Spark of Life. From molecules to cells. The origin of life on Earth is one of science's greatest mysteries. How did inanimate matter give rise to living organisms?
While we don't have all the answers, we know that life emerged from non-life through a process called abiogenesis. This process, occurring over millions of years, involved the formation of complex organic molecules from simpler inorganic ones.
Imagine early Earth's oceans, a primordial soup of organic molecules. Energy from lightning strikes, volcanic eruptions, and the sun provided the spark for these molecules to interact and form more complex structures. Over time, these structures became enclosed in membranes, forming the first cells.
These early cells were simple, single-celled organisms, but they possessed the remarkable ability to replicate themselves. Passing on genetic information from one generation to the next, life had begun.
Section 5. Life explodes, the Cambrian explosion. This is going to blow your mind. The Cambrian explosion.
For billions of years, life on Earth remained relatively simple, consisting mostly of single-celled organisms. Then, about 540 million years ago, something extraordinary happened. The Cambrian explosion.
During this period of rapid diversification, a dazzling array of multicellular organisms evolved, dramatically increasing the diversity of life on Earth.
The Cambrian explosion was a pivotal event in the history of life. It marked the emergence of most of the major animal phyla we see today, from arthropods to mollusks to vertebrates. The oceans teemed with bizarre and wonderful creatures, many of which would later evolve into the animals we know today.
This explosion of life was driven by a complex interplay of factors, including changes in ocean chemistry, the evolution of new body plans, and an increase in ecological opportunities.